educational background, he received his bachelor's and master's from Mississippi State, bachelor's in chemical engineering and master's in environmental engineering. He has supported and led research pertaining to water treatment, material science and engineering, analytical method development, and environmental sensing. Mr. Grotowski is a registered professional engineer in the state of Mississippi, and also served as the former vice president of bachelor's in chemical societies and master's in environmental engineering. Without further ado, I'd like to introduce he has supported and led research material science and engineering, analytical method development, and environmental sensing.
Kind of interesting to see the room entirely filled, but I appreciate you guys coming. I'll go ahead and get started here. So as Brooke said, I've been here since 2014. I'm in the environmental engineering branch. I've given several tours of the environmental engineering branch, our facility, so I'm comfortable talking about everything that we do. Just an overview as to what I'm going to be talking about today. I'm going to give a quick overview as to the branch in general. Talk about the personnel that we have. We have quite a few people from the environmental engineering branch in the audience today. Obviously Brooke, we've got a few others over here as well. Give an overview of the personnel, the facilities, and then kind of go into a case study as to some of the research that we actually do, more of a deeper dive, but keeping it still surface level as far as the research is concerned, highlighting one of the bigger topics that we've been working on for the past few years now, and that a heavy, I guess, large amount of researchers within our branch are supporting. I'm going to keep it kind of surface level just to make sure that people, their eyes don't glaze over and you guys fall asleep on me. But we'll get started on that. So as I said, the environmental engineering branch, we're one of the 9 branches within the EL. We're in the environmental processes and engineering division. A lot of the work that we focus on in particular is environmental treatment and scale-up technologies. So when I'm talking about environmental treatment, I'm talking about military contaminants and also civil works, contaminants as well. Treatment in water matrices, also soil, groundwater, all kinds of things like that. A little bit of modeling capabilities as well. And like I said earlier, we do work at different scales. So start at the laboratory scale and then scaling it up and beyond that. So in regards to our technical expertise, the folks who actually, run these experiments, we have about 34 researchers within our branch. Several of them have PhDs, many of them have masters, others have bachelor's degrees. Their backgrounds, include chemical engineering, like myself, chemistry, physical science, civil engineering, environmental engineering, biology, soil science, if I haven't already said that. So you can see basically the majority of STEM programs, science and engineering, we have representation to help us solve the problem. Most of the work that we do is in building 3297. If you guys are not familiar with that facility, it's just down the hill over that way next to the environmental chemistry branch and also kind of close to the UROC as well. Our facility is fairly large. We have smaller scale wet labs, I think 9 of them in total. Wet labs, when I'm talking about that, I'm talking about the bench scale experiments, analytical equipment in there as well, HPLC or high performance liquid chromatography, ion chromatography, IC. Gives us the capability to analyze organic contaminants being things like explosives, other military contaminants similar to that as well. We also have, I said, IC, so breakdown products or salts, ions. We also have capabilities to study metals with our ICP, UV vis, a lot of different technologies. We've developed methods to run them. We also, like I said, we're conveniently located right across the street from the chemistry building. So if we have, if we need more expertise to, run more specialized analytical we could just go across the street and work with them. But other than our wet labs, one of the things that really differentiates us as well is that we have a larger pilot scale facilities as well that allow us to build larger units. Pictured here toward the bottom is our DET system, the decontamination effluent treatment system. That's one of the projects that we worked on in the past few years. We actually developed a mobile water treatment plant specifically developed to treat decontamination effluents, so CBRN contaminants, chemical, biological, radiological, and nuclear contaminants that you may expect during certain attacks. Treating waters that are contaminated with that to make sure that they could either be used for reuse or other, or discharge. We've also been working on PFAS, developing water treatment systems similar to that. PFAS, for those of you who are not familiar, perfluorinated compounds, basically Teflon, but for military use. In a lot of different technologies the Army has been using and the military in general, and it's become kind of an issue, and we're really trying to get at the forefront of treatment in regards to that. But a lot of the work that we do, as I said, we scale up our technologies, so we really operate, the majority of our stuff is in the 6.2, 6.3, 6.4 realm, if you guys are familiar with that. So using applied sciences to either find the reaction mechanisms or reaction kinetics, and then building up from there to make either smaller scale prototypes that we can demonstrate or larger scale prototypes that we can actually take to the field. As I mentioned, the DET system has been used several times in the field. The perfluorinated system, the PET system that we've developed based on that is in the field right now. Or it's being shipped to Japan right now, actually, for field use in the next month or two. All of that's kind of in the 6.4 realm. We partner with a lot of universities and external partners as well to help us build these units and help us really commercialize or transition it out once they've been effective. So as I said earlier, I'd like to go into kind of a case study of some of the work that we do within the branch, a lot of the work that we've been focusing on a lot lately, and when I say lately, I'm talking about probably since 2015 and beyond currently. A lot of that work is involving graphene and graphene oxide. Is anybody familiar with those technologies? If you are, could you please raise your hand so I can get a kind of a lay of the land? All right, for those of you who may not be familiar with graphene, graphene is single layer graphite, essentially, single layer carbon. It was actually found quite a few years ago, and the people who discovered it got the Nobel Prize in physics, I believe, or something. And the way how they discovered it basically is they took pencil lead, graphite, they put Scotch tape on top, pulled it off, put it under a microscope, saw something that looked like chicken wire, said, hey, that looks pretty cool, I wonder what we can do with that. Several years later, people are doing things with that. We're finding the applications for what it is and finding out just really all of the capabilities that we can have by using that technology. And the reason why we are interested in it is because it's really capable of providing a lot of different benefits, not only to just the scientific community, but also to the Army and the military in general. Some of those benefits for application include water treatment. I'm going to go into a lot of detail as to how we're using them for water treatment. Also mechanical properties, so how strong they are, how flexible materials using graphene incorporated in them are. Thermal capabilities or thermal properties, we're kind of looking at that as well, and same thing with electrical. We're kind of potentially getting into that as funding, permits. But yeah, we've been working on that for quite a few years now. I've actually got some samples of different things. I'm going to pass them around the room real quick here to get an idea of what we've been working on. So I've got some membrane technologies here, if you could just kind of pass that around. I'm going to go into details regarding the membranes here that are being passed around. I've also got some, put that down for a second, polyurethane foam incorporating graphene in it as well. Split this up. You guys can pass these out. A lot of these samples are similar. You guys can pass them around, get an idea as to what I'm talking about. And I'm going to go into the technology for each of the samples that I just passed out. So if you guys are confused, hopefully I'll be able to address those concerns, and then we'll have a question and answer afterward regardless. So for water treatment, we typically use graphene oxide, which is oxidized graphene. Basically, it's graphene, like I said, the single layer carbon, but it's got little epoxide groups and little oxygen groups sticking out as well. Gives it a little bit more functionality. And the way how it works for the most part is if you make membranes out of them, the chicken wire lattice, essentially, that I mentioned earlier, kind of layers up on top of itself in kind of a unique way that allows for water to pass through, kind of zigzaggy through the layers, but larger contaminants are not allowed to. So if you have organic contaminants such as, like, in our case, explosives, TNT, or insensitive munitions, they're too big to really go through that lattice and they get blocked out. There are other mechanisms as well, such as charge repulsion or adsorption. The hydrophobicity of the graphene, or the graphene oxide in this case, can suck up some adsorbents, and because it has a negative charge, it can actually repel certain charged contaminants. And what we're doing with this graphene oxide, we're actually cross-linking it with chitosan. If you guys are not familiar with what chitosan is, it is a biopolymer that comes out of shrimp shells. It's actually like the second most abundant biopolymer in the world, behind cellulose, which obviously comes from trees and plant products. But one thing that's great about chitosan is that it's basically treated as a waste material because, shrimp shells are, for the most part, somewhat useless. Or at least we think of them as it's useless, so it's very cheap. Graphene is somewhat expensive, so if you mix a super cheap material with a somewhat expensive material, then you have a somewhat cheap material, so it's effective for transitioning out and being cost effective. And based on the positive charge you have on the graphene, or on the chitosan, and the negative charge of the graphene oxide, they kind of link together. Positive obviously attracts negative, and they stick together, and we're allowed to actually make membranes out of it. And when I'm talking about the membranes that we make, we've actually been, when I say we, our branch, and ERDIC in general, I guess, has been the first group in the scientific community who's actually been able to make scalable membranes out of graphene, or graphene oxide in this case. We've applied for a patent. It's actually been allowed, should be granted, and should be awarded pretty soon here. It's one of the at least 2, maybe 3 patents regarding graphene oxide membranes that we've developed that is in the process of getting awarded or has already been awarded. And when I say it's scalable, most of the research that's been done worldwide regarding graphene in terms of water treatment has been confined to a 47 millimeter disc, circular disc. And for those of you who may not be familiar with how small 47 millimeters is, that's about 1.5 inches. We've been able to scale it up to, most of our experiments are about 7 by 12, so about the size of like an iPhone. But we have also run experiments at a much larger, this is about the size of like a desktop. So maybe about the desk that is right in front of you. That's about the size of the membranes that we've made as large for experimentation. And I'll get into some of the details later on as this goes on. Another one of the things, as I've said, we're really doing groundbreaking research in regards to graphene, is that we're also the first group that's ever done cross-flow experimentation regarding membrane technologies. So for those of you who may not be familiar with membrane treatment or membrane use, when I'm talking about cross-flow, layman's terms, I'm talking about water passing across the membrane as opposed to going straight through it, which is known as dead-end flow. Cross-flow is used in the membrane community. It's actually when you hear reverse osmosis or membrane treatment, most of the water is treated using a cross-flow system. So for us being able to do it in cross-flow, it's much more applicable scientifically to an actual application rather than just for scientific interest. We're the first group, like I said, to be able to do that, so it's kind of a big win. We've published a paper on it. It's been cited several times. One of the organic simulants that we've used to kind of prove the effectiveness on it has been methylene blue. The reason why is because it turns water blue. So you can easily see that when you have a blue inlet and a colorless outlet, that you are blocking out your methylene blue and you're actually treating it pretty well. So we've looked at it. Methylene blue is a positively charged material, so we've been able to understand how positively charged materials react when they're put in contact with the membrane. as you can see, we've had extremely, just from these pictures down here, without showing any of the actual like data that we've collected other than visual, you can see that, we've been able to treat the water. There's a little bit of a pressure dependence here, but, at higher pressures that you would actually operate in the field, you were able to treat, 100% of the water, pull out 100% of the contaminant. We've also looked at a negative base dye to kind of understand how negatively charged materials affect the membrane or are impacted by the membrane. We still get some pretty good success, just maybe not as much color removal. Certain membranes that we've made with one grade of graphene oxide have given us almost 100% blockage. Other grades of graphene oxide, maybe not as much, but still pretty effective. This is some of the analytical data that actually shows it, 100% removal. This is the flux being the amount of water that actually passes through per square meter. It's kind of the, gold standard for understanding how much water passes through your membrane, the flow rate through it. But this is just, like I said, analytical data. The pictures actually speak for themselves. As I said, we've been doing a lot of scale-up work with these membranes as well. These are some of the pictures. This is Jose Matei Sosa and Victor Medina. Victor Medina was actually leading the DETS project that I mentioned earlier, that ultimately this project regarding graphene oxide and really all of our graphene research has kind of come as like the daughter of that project, for lack of a better word. So they're two members in our branch. If you haven't met them yet, I'm sure you guys will at some point in your career here. But yeah, this is just a membrane that we developed, or a system that we developed from the machine shop. Developed a membrane. You can see that's pretty large here. It's actually one of the largest graphene membranes probably ever produced in the world. We were also the first one to ever create it in a spiral wound fashion. And that's important because spiral wound membranes are actually how they're used in the field. They're provided in spiral wound format. So instead of having just a long flat sheet that would take up a lot of space in a treatment plant, you wind it up into a spiral. You can fit a lot more surface area into a small space. We've been the first ones to ever do that. So that's another big win in regards to advancing the technology of graphene oxide membranes and membranes in general. Another great thing that you have regarding graphene oxide membranes that we've been developing is that they're also easily recyclable in terms of being able to repair them. So for traditional membranes, say reverse osmosis membranes or nanofiltration membranes that are actually used as part of typical water filtration, if you tear your membrane or if anything perforates it, it degrades in any way, you have to throw it out, you have to buy a new one. The membranes that we've been able to develop here, if you do a treatment step, basically put it in acid solution, I think vinegar, acetic acid, process it in a certain way, you can repair your membrane, stick it right back out and, in the field, get the same performance as you would before it got damaged, which is very important. We've actually got one of our patents that's been awarded is for this technology, just because it's so useful, or it potentially has a lot of use if this technology gets commercialized. It really would cut down on capital cost for anybody who would go forward with that technology. Another thing that's great about graphene oxide membranes is that they have this anti-fouling characteristic. When I'm talking about anti-fouling, I'm talking about prevents biological growth. As you can assume, in areas where your water may have bacteria in it, obviously, like if you're pulling surface water out of a lake or a stream or something like that, it's obviously dirty. That's why we don't drink out of directly from a lake without treating it first. That bacteria has a tendency to grow on membranes. It actually, and as it grows, it kind of blocks the membranes, makes it less effective. Water can't go through. Well, the reactive oxygen species and just the way how the graphene oxide is set up, as I said, it has a lot of oxygen groups affixed to it. Those react with the biological cultures, break them down, and keep it from actually having that biological growth. So it's potentially a big advantage that graphene oxide membranes would have over traditional membranes when this technology goes forward and gets transitioned. Just a better example as to how well the graphene oxide works. One contaminant that we've dealt with has been cyanobacteria. I'm sure most everybody in the room is familiar with harmful algal blooms or HABs, blue-green algae, whatever you want to call it. It's a big issue you'll hear about, every summer in the, say in the Gulf of Mexico or around Florida. You always hear about these harmful algal blooms. We deploy a lot of people down to, help with Jacksonville District or whomever to kind of prevent them or manage them. Well, we took some cyanobacteria, contaminated water, added graphene oxide membranes, cut up some strips and put it in there and saw what it did. And what we saw was that, when you start out with this algae contaminated water, you stick the membrane in there and all of the algae sticks to the membrane, essentially, or it gets sucked out of the water, sticks to the membrane, and then over time, the oxygen groups that are on the membrane start to break it down. So not only is it sucking out of the water, it's also killing it at the same time. I can show you guys, I don't have any pictures right now, but if you guys are interested, we could share some pictures where you see like a cyanobacteria cell beforehand, and then afterward it's all busted up and obviously, damaged. So we have like actual qualitative data that shows that this is how effectively this is working. Another control sample that we've made, we've impregnated it with silver nitrate. Silver nitrate's a common technology used in disinfection. I believe there's silver nitrate or something like that, say, in your shoe soles. That's why they don't smell so bad after you wear your shoes for a certain amount of time. But if you put them in the washing machine and then take them back out, they start to stink afterward. And it's been just as effective. I've got other data as well. I'm not going to show that here, just in the interest of time. That shows just how effective our membranes are compared to the gold standard, like I said, silver nitrate. But moving on to some of the other things that we've been doing. So a lot of the work that we've been focusing graphene oxide on as it relates to the environmental engineering branch, basically, I guess, traditionally what we do in terms of, like I said, environmental treatment. I put a heavier focus on that, but we also do a lot of work outside of our traditional, I guess, capabilities in terms of, and when I say we do work outside of that, we do a lot of work with the geotechnical structures branch, lab as well, particularly their airfields and pavements branch and also concrete materials branch. Obviously, we're doing material science here when we're talking about graphene and graphene oxide. So understanding other capabilities, not just water treatment, that we can potentially provide, with this technology is what we're going after, funded this year and hopefully for years to come as well. One of them is polyurethane foam. That was the hard sample, like the circular disc that I passed around. Hopefully everybody got to see it and got to feel it and understands what I'm talking about here. Polyurethane foam is a common material, typically used. Typically, when you think of polyurethane foam, you're either thinking about insulation or couch cushions. That's softer, open cell foam, but if you make certain formulations of it, you can make it a lot harder and actually turn it into basically, in layman's terms, easy way of explaining it, expandable concrete. It's very strong, it's very hard, very rigid, but it also expands. A lot of the technology that we've been looking at is expanding about 5 to 6 times its original liquid weight, or liquid volume. So that cuts down on logistical burdens as you can think about storage and also shipment, across the world, as it supports the Air Force or the Army when you have to repair runways or airfields or any place where you would theoretically need a structural material like that. Storing concrete or similar materials takes up a lot of space. It also takes up a lot of, shipping logistics. So cutting that down, the Air Force is very interested in that. Another thing that's great, like I said, because it expands, is that's a lot more lightweight. So if you're getting a strong material that's lightweight, helps you benefit in terms of vehicular transport potentially. There are certain motor companies right now. I believe the Ford Motor Company is actually using polyurethane foams impregnated with graphene in their engine parts to kind of make them a lot more lightweight. So instead of using steel or metals that could be heavy, you're using these foam materials that are lightweight and still getting the job done. And then you save on weight, obviously, and you save on gas mileage. The Army is interested in that as well. Obviously, 2 of the 6 modernization priorities that the AFC is looking for right now are future vehicle, vertical lift, and next generation combat vehicle. And if we're talking about lightweight materials that could help with easier, lift off, more fuel efficiency, this would fit in both of those categories, these graphene foam materials. So an update on kind of where we're at with this. Like I said, I actually have some handheld samples. We're funded this year, and potentially, you know, in future years as well, expanding this capability of graphene and foam. All of our processes right now, or all of our samples are kind of currently being evaluated, not just for strength, but for thermal properties and things like that as well, to really understand what capabilities the graphene is providing the foam, kind of getting the full suite of it. And we've been analyzing in a lot of ways. We've got some SEM images over here. Obviously a bunch of different, this is foam without graphene. It disperses pretty well. That's why you see the uniform color. And obviously you guys have seen the handheld samples. One of the other things that we're doing with graphene right now is also in support of the Airfields and Pavements branch. Our collaboration with them is developing pavements that actually have graphene in them. So asphalt or graphene-based asphalt. You have asphalt with graphene in it. And the reason why we're looking at that technology specifically is that asphalt it's a porous media. Obviously, we're all familiar with it to some extent, and it also oxidizes and degrades when exposed to air. So if it's porous, air can penetrate through. The oxygen groups in air, or obviously there's a lot of oxygen in air, it degrades that asphalt, and I'm sure everybody here has driven in Jackson at least once and seen how bad the road conditions are over there. Anything that we can do to preserve our integrity of our roads, the Army, the Air Force, whomever uses a road, the military, and then not just the military, but you know, the country in general is very interested in using that technology. So the graphene would prevent air from penetrating through. All of the degradation would happen at the surface level instead of actually going all the way throughout. Really would help preserve the longevity of the asphalt. This technology is currently being used actually in Italy. So there is proof that the technology, you know, has legs. We're trying to evaluate it here and seeing just how effective it is. So we've been developing this is an in-house technology that one of our researchers is working on, where we pump basically air or, you know, oxygen through the system and then measure what comes out on the other end to kind of understand what's being blocked out, how much air is passing through. Obviously, we're, you know, measuring this against control samples that don't have graphene in it as well to really see how effective that is. Jose Mate, whom I talked about earlier, is actually leading that study. And Chris Griggs, who is really leading a lot of the research that we're doing here regarding graphene, is also involved. So just in summary of, you know, today's seminar, the environmental engineering branch really works to develop world-class products that are smarter, faster, and better, actually transitioning those out. We do a lot of work incorporating a lot of expertise, all scientific, you know, taking it from lab scale to, you know, to field scale and actually taking these technologies out of, you know, out to the field. And obviously we've been doing a lot of groundbreaking research with graphene and graphene oxide and related materials. Some of the technologies that we have, you know, up here for display, I didn't really get into a whole lot of the civil works stuff, but we do, as I mentioned earlier, really focus about half of our energy is focused on civil works mission as well, sediment management, things like that. This is a picture of the DET system that I mentioned a few times, and then also a system that we developed for polyurethane. As I said, it's a pretty strong material. This is myself, Chris Griggs, Marielle Magias from GSL, and then Jared Johnson, who used to work in our branch, standing on it, so you can see that it's a fairly strong material. Some of the acknowledgements, branch chief is Amy Poda, if you guys are not familiar. She's our acting branch chief right now. Andy Martin is our permanent branch chief when he's not doing detailed assignments. Technical personnel working on the graphene work, all the stuff that I basically showed you guys today. As I said, Chris Griggs is kind of leading The majority of the work that we've got right now, he's this fellow right here in this picture. Victor, like I said, he started the DETS project that ultimately opened the door for graphene research. Jose, Jacob Lally, he's one of our newer hires. He's been here for maybe a year and a half. He's a civil engineer. He's been doing a lot of the work regarding foam. As with John Brazier, he's been here for a year, probably to the day. Chemical engineer who's been working on the polyurethane project as well as it relates to graphene. Kate Noel, she's in the audience. You could raise your hand for those of you who may not know her. And then Sarah Grace as well. They've been working heavily on the graphene membrane stuff and also some of the foam as well. And I think that's about it. Any questions?
So we can open up to questions. We also wanted to we know there might have been some glitches and stuff, and we want to hear your feedback to make sure that this was beneficial for you. So there is a survey that you can, if you go on menti.com and type in that code, you can fill out that survey, and that'll help us make this better.
Can we send that out to everybody, the link?
Yeah, we can send it out as well, and we'll leave it open. So, and then feel free to come to us if there's anything as well. There's also snacks, and don't forget to sign in, and then we can take questions.
Apparently Brooke made the muffins that are over there by hand, so yeah.
Can you talk real briefly a little bit about how you built the project? Like, is it internal funding that you transitioned to small reimbursable projects, or how did that all work out?
Okay, yeah. So, a lot of the work that that I showed up here originally started as direct funded projects. So, the DETS project, which had a small section of it that involved, next generation membranes that ultimately opened the door and paved the way for graphene. That was a direct funded project, 6263, funded with EQI funding. Since then, so the funding right now that we're dealing with regarding graphene is through the fifth project, or fifth program, or whatever they call it now, 219, Flex 4, has a bunch of different names. It's an ERDIC funded program that actually is funded, I believe, with it's part of your burdens that you pay goes to the headquarters, then it goes out to build capabilities across ERDIC, and that's what we've been doing. We've also been working hard to bring in congressional funding. That's where, when I kept saying, hopefully for the next few years as well, we've been putting in proposals for congressional work to bring in more funding regarding graphene for the next 4 or 5 years or so. Does that help answer your question?
Yeah. Luke, do we understand what, and maybe everyone knows this but me, but do we understand what graphene does to organisms? Do we understand what graphene does to organisms in the soil? Are we going to be developing a graphene filter to get out of the groundwater in 10 years?
I mean, it's possible that we could use that, technology in years to come. Like I said, well, I guess maybe I didn't say this. Those evaluations are ongoing right now. What materials are actually being, or what microorganisms are actually being degraded. It could be a potential use in the future. We're doing that research right now. In terms of putting it in the soil, I'm sure there's a way to make that happen. Treating groundwater in a pump and treat type way.
Do we want it in the soil if we're putting it in asphalt? What are the second and third order effects?
For the most part, graphene is like inert to humans. So, I don't think it would cause any problems if we were to put it in the soil. We haven't done that, so I can't say for sure. But I don't see really what the downside from a risk standpoint would be. But we could potentially do that. One of there may be other technologies that may be more cost effective. Graphene, as of right now, is fairly expensive. But there are several organizations or several companies in the private sector right now that are developing new ways to create graphene, and we're actually partnering with them as well to get more cost-effective, cost-efficient graphene that make it more abundant and applicable, I guess more feasible to being used in technologies where we do see the benefits like what I mentioned earlier.
Hello? Okay. I was curious about airflow through graphene. So most of the things you were talking about were water-based.
Right.
So I'm just kind of curious if you could use it for a better face mask or a better air purifier or
Yeah,
something along those lines.
that is one of those things that we have like on our list of things to do, but we haven't prioritized it yet to really understand the air treatment aspect of graphene. We think that it would be effective, but we haven't run any tests yet to actually show that it would be. Hopefully, you know, if not this fiscal year, in the near future, we would be able to run those tests. We have the capability to do it. We just haven't had the time, I guess. But we do think that it would be effective for the most part.
Any other questions? All right, thank you guys so much for coming. Our next seminar will be next Wednesday. Yes. So same time, and I think place as of right now. We'll send out an email. Yeah, we'll send out an email if the location changes. But one of the other branches will be presenting next week. So thank you guys for coming.
You're pretty good for the whole set.